in order to solve this with matrices, we're going to need our system written as a matrix vector equation. So the first thing we're going to do is write that out. We're going to have some matrix times our coefficient vector x1, x2, x3, and that will equal some vector. Now this vector is on the right side of the equation, and here on the right side of the equation all we have is 1, 2, and 3. So it should be pretty clear that that's what we should be getting. On the left side of the equation we have a matrix multiplied by this coefficient vector gives each of these different equations from each of the 3 different rows. Now when we multiply this matrix by this vector, we're going to first take the top left element times x1, the top middle times x2, and the top right times x3 and sum them up. That looks exactly like this, but the things that get multiplied by x1, x2, and x3 are just these coefficients here. So that would be 1, 2, and 1. Similarly, for the middle row, it'll be the coefficients of the second equation, -1, 4, and 3. And for the last row, it'll be the coefficients of the last equation, 2, -2, and a. We can write this as b x equals c, where we have the obvious correspondence here. Now, b is not a constant matrix, right? It depends on the value of a. And what we want to look at is how does the number of solutions to this linear system depend on the value of a. In other words, how does the number of solutions to this matrix vector equation depend on the value of a? The way we determine that is by asking whether or not b has an inverse. If b inverse exists, then we can just multiply it to each side here, and we'll just have x equals b inverse c. Since b inverse is just some matrix and c is this particular vector here, their product will be just one vector. You'll have a unique solution. So this is the unique solution. Otherwise, there's not a unique solution, right? There could be there could be more than one solution. Usually that means an infinite number of solutions, or there can be no solution. So otherwise, there are infinity or 0 solutions, right? But we're only interested in determining when does it have unique solutions. So when does b inverse exist? Well, b inverse exists is an equivalent statement to determinant of b is not 0, right? Determinant of b, 1, 2, 1, minus 4, 3, 2, minus 2a. We can calculate this just by calculating determinants on the minors, making sure to alternate our signs. So we'll have 1 times the determinant for 3 minus 2a, of minus 2 times the determinant minus 1, 3, 2a. Oops. And then we'll have 1 times the determinant minus 1, 4, 2, minus 2. We can calculate this to be 2 minus 8, which is minus 6. This is 4a plus 6. So these will cancel out. This will be minus a minus 6. With this minus sign, it would be plus a plus 6. And with the 2, it would be plus a plus 2a plus 12. So plus 2a plus 12, which is 6a plus 12. And this is not equal to 0 as long as a is not equal to minus 2.